Okay, this first lecture for Chapter 10, this is part 1. Chapter 10 is all about, or part of Chapter 10 at least, is about hypothesis tests about the population mean. And this part, or this lecture, is going to cover Z-test. So let's review. Sampling distribution of X bar, the sample mean. If a simple random sample of size n, so there's the randomness assumption again, it's in almost all of the hypothesis tests that we consider, and nearly all the inferential statistical methods depend on random samples. So we have a random sample of size n, and it's taken from a population having population mean mu and population mean or population standard deviation sigma. If the original population is normally distributed, then the sample mean is normally distributed with a population mean mu and a standard deviation that's been adjusted by dividing the population standard deviation sigma by the square root of n. And this symbol should be a square root. And I don't know, there's a couple of little anomalies in my PowerPoint because the PDF file I'm using to screen capture these images was messed up, and I don't know why. But in any case, now, notice that we have the standardization transformation. So the focus of this lecture is on standardizing the sample mean. So here's yet another form of this transformation, because now X bar is being subtracted from, or mu is being subtracted from X bar here instead of X. Yet the transformation still leaves a standard score or a standardized value for the sample mean. Z is always normal, and specifically it's always the normal distribution with mean 0, standard deviation 1. That's why we call it the standard normal RV for random variable. So Z is standard normal always. Okay, now second part. If the original population is not necessarily normally distributed, meaning that it's maybe skewed to the left or skewed to the right, but the sample size n is large enough, our standard for large enough is any sample at least 30, n is greater than or equal to 30, then X bar is approximately normally distributed. This is the central limit theorem that is, the reason for this is the central limit theorem. And again, it's the same transformation. See, these are square roots here, square root of n. Let me just clarify. And this is also square root of n, okay? So either way, we use the same transformation, standardization transformation. So we do have a sample size consideration now. If we're going to model the mean using the normal distribution, then we need to have a sample size that's at least 30. Or we need to have reasonable assurance that the population distribution is normally distributed. Let's take a look at an example here. Farming salmon. So a salmon farming operation is interested in determining if a new type of pellet food will improve the average yield of salmon product. Past samples indicate a population mean yield of 15 pounds with a standard deviation of 2 pounds. A sample of 50 salmon that were raised on the new pellet food had a sample mean of 16.2 pounds. Does the data provide evidence of an improved yield of salmon product? Conduct the appropriate statistical hypothesis test. So here's what we have. Theory. The theory is the new pellets will increase the yield. That gives us the following statistical hypothesis. The null is status quo. Status quo is new pellet, no better than old pellet. That's what the status quo assumption is in the null. And the alternate is where the theory goes. And the theory is that the new pellet increases yield. And notice that what we're saying by and again, I've translated the theory in the status quo theory into the hypothesis using the parameter value, because statistical hypotheses are always about parameters. Now, how are we going to model this? Well, we were given in this problem mu and sigma. We also have a large sample. N is bigger than 30. N is 50. Okay, so 50 is n, which is greater than or equal to 30. That means we're going to model x bar, or that we can assume reasonably that x bar is normally distributed. Hypothesized means 15 pounds, and then we're going to adjust the standard deviation because of the central limit theorem. Ultimately, to make a decision here, we're going to want to know what the p-value is. So, one way to calculate the p-value would be to use x bar's natural distribution, which is going to be normal. So I'll label this axis with x bar. And distribution centered at 15. And let's see, let me just put a few more numbers here. So like maybe 17, 19, 21, just to give a scale here. Let's see, 2 less than 15 is 13, 11, 9, okay. So, here's what we're looking for. Excuse me. Our sample mean was 16.2, okay? So 16.2, I'll put that right about here, okay? 16.2. So the p-value is going to be the area in this right tail of x bar's normal distribution, okay? And so we could calculate the p-value using normal CDF. Lower limit here is 16.2. Upper limit is positive infinity, which of course is not a number, so I'm going to have to use E99 there. Then we have 15, and we have 2 divided by the square root of 50. So that will give us the p-value. Or another option is to use the z transformation here, okay? So the specific z transformation for this example is going to be x bar minus 15, that's mu, divided by sigma divided by the square root of n. And I don't have my calculator. If I go to my calculator, I'll lose everything I've written here. So I'll do that. I'll do this calculation when we get to the TI here. So 16.2 minus 15 divided by 2 over the square root of 50. I'm not sure what that specific z value is right now. But let's go ahead and let's go to the calculator and calculate that. So let's see. Here's the calculator. So first thing I want to do is calculate the area using x bar's distribution. So let's see, that was second var's normal CDF 16.2 comma E99, comma 15, comma 2 divided by the square root of n. So the P, oops, I keep doing that. Hold on here. All right, I do not want the parentheses there. Got a right arrow. There we go. So the p-value here is pretty small. It's about 0.00001. And while we're on the calculator, let's calculate the z-value. It was 16.2 minus 15. That whole quantity is going to get divided by the quantity 2 divided by, oops, wait a minute now. What am I doing? 2 divided by square root 50. So the particular z-value we're talking about here is about 4.24. So we already know the p-value. The p-value is approximately 0.00001. Okay, and I was using x bar. That was using x bar x bar is natural. Well, what sometimes I like to think of as x bar is natural distribution or normal distribution. But we also did the z transformation, and we'll just rewrite this. 16.2 minus 15 divided by 2 over the square root of 50, and that calculation yielded about 4.2 adjusted standard deviations. Now, the cool thing about that z transformation is that, again, remember, the z-score is the number of standard deviations, adjusted standard deviations in this case. So what we're seeing is that that sample mean was over 4 adjusted standard deviations from the hypothesized mean. That's going to trigger a rejection, because that tells me that fact that that's so many standard deviations away makes it very rare and unusual. So again, what I want to do is rescale, or not rescale, but I'm going to put some scale on the axis here. So again, this is not, and also notice I labeled this axis with z, because now I'm talking about the z distribution. So 4.2, say, I'm just going to round that to 4.2. 4.2 is right about there. So the right tail area under z to the right of 4.2 should be about the same value. So another way I could calculate the p-value is using normal CDF again, but now I'm using the standardized distribution, or the standard normal distribution. So now the upper limit is going to be 4.2, still positive E99, because this distribution also, this tail also goes to positive infinity. But now the mean is going to be 0 and the standard deviation is going to be 1. So when I go back to the calculator, okay, second vars to the distribution menu, normal CDF, lower limit's 4.2, upper limit is going to be E99. And interestingly, all of these commands on the calculator have what we call default settings. And the default setting for normal CDF is a mean 0, standard deviation 1. So normal CDF defaults to standard normal. Now I got a little bit of round off error here, and that's because when I did the z calculation up here, I rounded that number off to right here to the 10th place. But again, I'm not going to worry about that because it still is very close to the original p-value I got above. So using the z transformation, going from the sample means distribution to the standardized normal distribution yields the same p-value. Well, let's see here. Okay, there's another example. I have one more thing I want to show you on this example. Um, we call this the Z-test, okay? Now, okay, so this is the formulaic approach. I don't know if I spelled that right. Formulaic, I don't know. I don't even know if that's a word. I'm not going to worry about it. Okay, so when we do the Z transformation here, okay, and again, I want to focus on the transformation for a minute because this is building up to a sort of a process approach to hypothesis testing. So one of the things you're going to notice about statistical hypothesis test methods is that usually they have two parts. There's the transformation part, okay, that's the Z transformation in this case, and then there's the distribution part, okay? So when I do the transformation, then what I'm doing is I'm taking the input variable, okay, so x bar is a variable, and then I'm getting a different output variable as well. They're both variables, but really what's happened to the Z here is it's been shifted and then rescaled. And it takes, and then we have to know and remember that Z is a standard normal variable, and that's Z's distribution, okay? So this is the formulaic kind of an approach to doing a hypothesis test. This hypothesis test is built into the TI calculators. And not all of the TIs, just the 83s and 84s have these built-in hypothesis tests. Technically, the 89 does, but the TI-89 does as well. But if you want to use the 89, you might have to download the Stats app. But I'm not supporting the TI-89. I just want to mention that. Okay, so but it is possible to use the 89 for doing statistical analysis as well. Okay, back to the calculator. Now, same place we found linear regression t-test under the stat menu, test menu, there's z-test right there. So if I select z-test, it gives me two options. I can enter raw data or I can enter the stats value, okay? And in this case, I have the x bar, I have sample mean, and I have the sample size. Now I have to input some information here. Mu sub 0, that's the hypothesized mean. In this case, for the example we just did, it's 15. Population standard deviation's 2. Sample mean was 16.2. Sample size is 50. And alternate, 3 choices. Not equal to, that's the two-tailed test. Direction of extreme, one-sided to the left. Direction of extreme, one-sided to the right. That's the one I want to choose. Then we say calculate. And what the calculator does is it prints out all of these statistical values. Notice there's the z-score, there's the p-value. And then again, it gives prints out the sample mean and the sample size. So more and more, as we go through the course, we're going to be looking at these automated kind of ways to do the hypothesis test on the calculator. But I think it's important to know what's going on behind the scenes. All right, well, anyway, you slice it here. We ended up the p-value. It's about 0.00001. That's a little sloppy. But in a nutshell, this is very small. It's a very small p-value. So what we would conclude is there's statistically significant evidence that the new pellet food increases yield. So that would be our conclusion. So we're rejecting the null hypothesis because of the small p-value and concluding that we have statistically significant evidence that the new pellet food increases yield. Let's take a look at another example here right out of the textbook. Let's do it 10.2. So experiments on learning in animals sometimes measure how long it takes a mouse to find its way through a maze. The mean time is 18 seconds for one particular maze. That's going to be the population, or the assumed population mean. A researcher thinks that a loud noise will cause the mice to complete the maze faster. The appropriate null and alternative hypothesis regarding mu, the population mean completion time with this noise stimulus, are there's the population, or the null hypothesis, mu is 18. The alternate is mu is less than 18. The significance level for this test is set at alpha equal 10%. The researcher decides to measure how long each of 10 mice takes to complete the maze with the noise stimulus. The sample mean time to complete the race for these 10 mice was 17 seconds. Assume that the 10 mice form a random sample and that the population of completion times with the noise stimulus follows a normal distribution with a known population standard deviation of 2 seconds. And then the observed test statistic is given as, and this formula is hard to read. I don't know what's going on with my computer here, but the format for some of this stuff is messed up. But basically, okay, the test statistic is given. Now I want to take a minute to talk about this term, test statistic, because this term will come up over and over again. The z value from the data, which in this case we're told is negative 1.58, this is what we call the test statistic. Then we take that test statistic based on what we know about its distribution. Again, z is standard normal, and we do the calculation. Now, since we're dealing with a transformed variable, I'm going to label the axis with z and scale the z-axis accordingly, or appropriately for this for the standard normal random variable z. Now notice I want to point out another thing here. The z-value is negative here, and it tells me the sample mean was to the left, so 17 is smaller than 18, and that's why the z-value is negative. But in any case, that z-value of negative 1.58 is right about here. And what's the direction of extreme? Well, I'm going to key off the alternate here, and I can conclude just by looking at the alternate that it's one-sided to the left. And that this is going to be more and more the way we look at, or the way we determine the direction of extreme. Even though, I mean, the definition of direction of extreme is a little more complicated than that. But it turns out for the hypothesis test for the mean that we can always look at the alternate, and the direction that inequality points in the alternate tells us the direction of extreme. So the p-value corresponds to that area in the left tail. And one way that we can calculate this, okay, is using normal CDF. Lower limit here would be negative E99. Upper limit is negative 1.58. And the default here is 0.1 for the mean and standard deviation. On the other hand, though, now we have, I've just shown you that this test is built into the calculator. So what we can do is go to the calculator, and I got to remember all these details here. So we're told that we have a population. So let me just summarize it here. So mu sub 0 is 18, sigma is 2, x bar is 17, and n is 10. So this is the information I'm going to need to put in the calculator. Now the other thing I want to make sure I point out here is we're given quite a bit here, and this is what's allowing us to use the z-test. We are given that the population's normally distributed, that's x, that's the variable x, and that we have a known population standard deviation, and that's italicized, because really that assumption's probably not reasonable. All right, so I'm going to go back to the calculator and show you how to do this on the calculator. So press stat, go over to test, choose z-test. Again, we have stats this time again. So the mean is going to be, the hypothesized mean is 18. The hypothesized standard deviation here is 2. The sample mean was 17. The sample size was 10. So we have a small sample here. It's not 30 or more, but see, we were given that the population was normally distributed. And what we end up with, oh, see, now look. All right, I made a mistake, and the p-value instantly told me that I had something going wrong. So my p-value is 0.94 here, but my z-value is -1.5. So that p-value is way too big. So where did I go wrong? I didn't use the right direction of extreme. So let me go back and show you what happened here. Back to stat test, back to the z-test. So I went right by this. So I entered all the numbers correctly, but I skipped right over the alternate here. And the alternate in this case, this is a direction of extremes to the left, so I need to pick the less than. And now when I say calculate, there's my p-value. It's about 0.057. So the p-value that we calculated is about 0.057 roughly, or 0.06, about 6%. Now we were told that the alpha is 10%, okay? So what's our conclusion going to be? Well, first of all, I'm just going to round to 0.06. 0.06 is less than 0.1. That implies that P is less than alpha, and that implies that we should reject the null hypothesis. So we're going to reject H naught. Now we're supposed to write out the conclusion in our own words that nobody with a background in statistics, or but anyone with no background in statistics would understand. So how can we do that? Well, first thing I would say, or one way to start this, is to point out that the data collected is very unusual given the assumption that the mean average completion time is 18 minutes, or 18 seconds, I should say, right? I think the units were seconds. Okay. So the other part of the conclusion, and the part where I would try to articulate it in such a way somebody with no statistical background would understand, is that I would say something like that these data provide statistically significant evidence that the noise stimulus decreases the average completion time. Okay, and again, there's always more. There are multiple ways to phrase these conclusions, but that's the basic idea. Now, here's the conclusion to this lecture. How can we possibly know sigma? Okay. Mu is not a problem. Let's talk about this for a second. Mu is not a problem. Why? Well, it's because when we're testing a hypothesis, mu is one of the null assumptions, like mu is equal to 18 in this last example. So in a sense, we'll always know mu because it's going to be assumed, okay? So mu is always known based on the null assumption, based on H naught, okay? Now, sigma generally is not known. This is really a big problem, because notice that in that Z transformation, the basis for the Z test, okay, and I'm going to put a mu sub 0 now, just that's kind of like that subscript is just emphasizing that mu comes from, the mu that we're using in this transformation comes from the null hypothesis. So we know the null, the hypothesized mean. Of course, we're going to get a sample, so we'll know x bar. We'll know the size of the sample, so we'll know n. But this is kind of a glaring problem. So one thing that is tempting is to replace that sigma, and notice I changed the equal sign to approximately equal to change that sigma to s. And the assumption that we're making here is that sigma is being approximated by s, okay? And then again, in either case, z, we know z's distribution because z is always has a normal distribution with a mean of 0, standard deviation 1. So again, we call this the standard normal distribution. So the real question here is whether or not this is reasonable. Is this approximation reasonable? Well, what's the answer to this question? This is where students sometimes really get frustrated with statistics, because the answer to this question is simply not clear cut. And my answer I'm gonna give to this question is this reasonable? Well, it's probably reasonable if the sample size is large enough, okay? So yeah, it's probably okay to do this, to make this assumption, and to go ahead and model Z using the standard normal distribution, as long as we have a sample size that's relatively large. But when n is less than 30, it's really not reasonable to say sigma is approximately equal to s. And in fact, the smaller the sample, the less reasonable that assumption becomes. So what do? That's part 2. So have a great day, and be sure to catch part 2 of the Chapter 10 lecture series.